A generator works based on Faraday's law of electromagnetic induction. When magnetic fields through a closed conductor loop changes, an induced electron force and thus an induced current are generated in the loop.
In an alternator, this process is achieved through the periodic movement of the conductor cutting through the magnetic field lines. As the coil continuously rotates in the magnetic field, the magnetic flux passing through the coil changes with the angle, thereby generating an alternating electromotive force with periodic changes in magnitude and direction within the coil, and ultimately outputting alternating current.
The generator has two basic structures. Either the magnet rotates while the coil stays still, or the coil rotates while the magnet stays still. Both ways work, as the change in magnetic flux produces induced electromotive force to generate electricity.
However, in this project, the neodymium magnets we are using are quite heavy. Rotating the magnets directly would require significant torque, putting a strain on the shaft and the drive mechanism. To solve this, we've opted for a stationary magnet and rotating coil design. This significantly reduces the moment of inertia, making the assembly much easier to drive by hand or with low power of our power generation system. To further boost efficiency, we've connected the outer side of the magnet using a strip of tin can metal. This acts as a magnetic yoke, providing a low reluctance path that significantly reduces magnetic flux leakage. By channeling the magnetic field more effectively through the coils, we can maximize the induced current.
Using a 20-meter enabled copper wire, which is 0.5 mm diameter, and a bottomless plastic cylinder as the bobbin, wind the wire tightly and evenly in a clockwise direction. After the first layer, without cutting the wire, return to the start and wind the second layer in the same clockwise direction. The induced magnetic field direction depends on both the current and winding direction. Opposite winding directions cancel the magnetic fields, greatly reducing the overall field and induced EMF. Consistent direction adds the fields together, boosting magnetic flux and generation efficiency.
We choose a cylindrical fan for following advantage compared with a rectangular fan. 1. The coil cuts magnetic fields lying more evenly when rotating, producing a more stable output voltage waveform. 2. The curved surface allows tighter windings of wires and improved magnetic flux utilization. 3. Symmetric mass distribution ensures smoother rotation and lower resistance. 4. Without shaped corners, it prevents damage to the emelled wire insulation and avoids interturn short circuits.
The rotating shaft is made of cylindrical wooden chopsticks, and the interior of the frame is filled with dishwashing sponges. The dishwashing sponges have good elasticity and are lightweight. They can not only firmly fix the relative position of the rotating shaft and the coil, but also reduce the overall load, making the rotation more effortless. The cylindrical structure can reduce the friction resistance during rotation, and the wooden material itself has a low weight. At the same time, the chopsticks have good insulation properties, which can prevent the coil wires from connecting with the rotating shaft wires, thus avoiding short circuits and ensuring the normal operation of the circuit.
Using wooden blocks and boards as our raw materials, we measure them out and assemble them with hot glue to create the generator's supports and the bearing structure. The wooden blocks position the shaft, keeping it spaced from the base to avoid connect friction. The bottom board supports the shaft to minimize rotational resistance, while the top board prevents the shaft from shifting or sliding out. The magnets are fixed as close to the coil as possible without touching, ensuring no friction interferes with the coil's rotation. We wrapped enamel copper wire with the insulation contact around both sides of the wooden channel to further secure the shaft's horizontal position.
I'm responsible for designing the wire leg structure. when the coil rotates. The directly connected external wires will get tangled. Therefore, I adopt a solution with two Cooper foils for current conduction. The two wires are connected to the two Cooper foils respectively, and current passes through the Cooper foils to external contacts, so as to prevent wire tangling. First, I used a knife to scrape off the insulating paint at the end of one enameled Cooper wire. I passed the wire under the first Cooper foil and wrapped the bare part firmly around the second Cooper foil. After that, I put a layer of paper tape between the first Cooper foil and the wire, to stop the Cooper foil from wearing off the paint and causing a short circuit when the coil rotates. Similarly, I wrapped the other wire with paint removed around the first Cooper foil and fixed it with tape, to keep the wire from falling off during operation. I kept a certain distance between the two Cooper foils and separated them with insulating paper tape, to avoid short circuits caused by contact between them. Finally, I installed simple Cooper rings at the Cooper foil positions fixed on the chopsticks, making it convenient to connect the external devices to the motor. This is the test data of our generator that we measured in the lab. We added a motor at the back to keep the generator spinning at a steady speed. Here are the readings from the oscilloscope. The frequency is 387.15 kHz. Its highest position voltage is 26 mV, and the lowest negative voltage is minus 38 mV. We also see an unwanted DC noise of 3.87 mV. The wave takes 666.6 nanoseconds to rise and 610.2 nanoseconds to fall. The total voltage from peak to peak is only 64 mV. We can clearly see two problems. The top and bottom parts of the wave are not the same size. The line of the wave looks twisted, and the generator doesn't produce enough voltage. Here are three ways we can fix and improve it. First, make both coils have the same number of loops and wrap them equally tight. Use magnets with the same magnetic force and shrink the space between the spinning coils and fix magnets. This will even out the magnetic field and fix the uneven wave shape. Secondly, put a capacitor into the circle to remove a 3.87 mV of extra DC noise. Thirdly, we can add more loops to the coils as long as the iron core won't get overloaded. We can also use stronger magnets, make the gap even smaller, and pick thicker copper wire to cut down the coil's resistance. All these changes will help us get higher output voltage and make the generator work better.